Next, we're going to look at angular momentum. Angular momentum is sort of the next rotational version of something we've already seen in a linear format. We've seen the concept of momentum and conservation of momentum before, so now we're going to look at that from the point of view of rotating bodies. A quick reminder before we get into it, cross products is another way of combining two vectors. We've looked at dot products before, and a dot product takes two vectors and it finds a number, a scalar, and that scalar is 0 if the two vectors are perpendicular. That's one of the useful things about it. A cross product takes two vectors and it creates a third vector out of it. If you've seen it before, A cross B, to calculate it, it's a combination of all the components of A, all the components of B to get a new vector. So I was going to do an example of that. You may have done this before. Hopefully I will do a couple examples, and then we'll see their usefulness. So real quick, let's just say vector C then is going to be A cross B, and I have two examples here, A and B, and we're going to take their cross product. So the way I like to do it is I set up a 3x3 array here like this to help me figure it out. And so the three components of the A vector are 3, -2, and 4, and the three components of the B vector are 2, 2, and 3. And the way a cross product works is first you calculate the I component. I'll show you that, and then you subtract from that the J component, and then to that you add the K component. It's always plus I minus J plus K. So for the I component, you hide everything under the I. You sort of ignore the two numbers underneath the I, and you cross multiply these two numbers here. So it'll be -2 times 4 minus 2 times 4. So that would be the I component, right? And then to find the J component, there's always a minus sign for the J component. Then you would cross multiply this times this and this times this. So for the J component, it'll be 3 times 3 minus 2 times 4. And for the K component, then what you do is you will hide everything under the K and you will cross multiply the remaining one. So for the K component, it'll be 3 times 2 minus 2 times -2. So in other words, it'll be 3 times 2 minus -2 times 2. All right, so when you work out the I component, it works out to be -14 I hat. The J component works out to be -1, and the K component works out to be 10. All right, so that's A cross B, which we're calling C, and this is a new vector. And one of the nice things about this is if I take the cross product of two vectors, one of the properties that a cross product has is that vector will be perpendicular to both the original vectors. So in other words, A cross B will be perpendicular to A, and A cross B will be perpendicular to B. So if you were to do the dot product of this, if I were to do the dot product, you can do this to show it, that will be equal to 0 because they're perpendicular to each other. All right. We could also, if we want to, calculate the magnitude of this thing. So that would be, -14 squared plus -1 squared plus 10 squared. That will work out to about 10.72 is the magnitude of that vector. So that's something that's going to come in handy. So remember, regular momentum is mass times velocity, and it's a vector that points in the direction of the motion of the object, and it's dependent on its velocity, on its speed, and on its mass. The angular version of that, so for the angular one, we want to measure something's motion around its axis of rotation, right? So if I have an object here at point A and it has a certain momentum in that direction, I want its angular momentum, basically its momentum around, let's say it's rotating around the z-axis. So what I need is the distance of the object from the z-axis and its momentum. So r is the distance of the object from the point around which we're calculating the angular momentum, and p is of course the momentum. And then this angle here, if I were to redraw the momentum at the origin, that angle here between p and r is handy. for calculating these angular momenta. So r points from the axis to the point, and we're going to find the angular momentum L. This is script L as a vector. It's going to be r cross p. Or one way to do the magnitude of a cross product is it's r times p times the sine of the angle between them. Or if you just write p as v, p equals mv, then we end up with this, right? We end up with, another way is, this would just be the magnitude, right? This is not the vector. So, and the magnitude of L could also be mRV times the sine of the angle between them. So this is our definition for the angular version of the momentum. It depends on its location with respect to the axis of rotation, or to the pivot point, and depends on its momentum. So we're going to investigate the properties of angular momentum. Note that it has units of kilograms, meters times meters per second, so it's kilograms meters squared per second. Or you could write that as joule seconds if you play around with the units. So the magnitude of that vector, as I said before, is r mv times the sine of phi. So if you know how far it is from the pivot point, the mass, the velocity, and the angle, then you can calculate the magnitude of the angular momentum. What's handy here is I can write mv as p, so mv sine phi. Basically, that's one way of saying that it's rm times the perpendicular component of the velocity, or the perpendicular component of the distance vector times v. So this is just one way to think about it. It's r and v and m, and either it's the whole r vector and the component of v that's perpendicular to r, or the whole v vector and the component of r that's perpendicular to v. Sort of two ways of seeing it. Let's do a simple example here. I have a 200-gram ball that's moving in the plus x direction as shown. Okay, so it's moving in the plus x direction, and I want to calculate its angular momentum around point P. So there's point P right here. I want to find the angular momentum around that point. So what's its angular momentum at this instant? So I need r, which is a vector pointing from the point to the ball, and you notice that this here would be the r vector, and that's just pointing along the plus z direction. So r is going to be 2.0 meters in the k hat direction. The mass is given as 200 grams, so let's put it in kilograms, 200 kilograms. The velocity, we're told, is moving along the plus x-axis, and it's 5 meters per second, so 5 meters per second in the I hat direction. So that means we can write down p, right? P is just mv. So 0.2 times 5, so we end up with 1.0 kilograms meters per second in the I hat direction. So now we have r and p, right? We have p, we have r, so we can use that to calculate the moment of inertia. Or sorry, the moment of inertia, the angular momentum. So the angular momentum is equal to r cross p. So let's do another example here of this cross product. So I put I, j, k here, and then I put the three components of r. Now you notice that r only has a k component. So 0 for the x component, 0 for the y component, and the k component is 2. I'll put in the sig figs at the end. And it has units of meters. I'm going to factor that out right here, make it a little bit simpler. Now for the third row, I put the components of the momentum. And the momentum is only in the I direction, right? And it's 1. So there's 1, there's no j component, there's no k component. I'm going to factor out the units again, and that's kilograms meters per second. So now I can do this. Calculate this angular momentum. So let's see. I is going to be, right, it's going to be this times this, because I cover the 2 under the I and I cross multiply the rest. So I end up with 0 times 0 minus 0 times 2. So that's going to be 0 for the I component. For the j component, you remember it's always minus j. 0 times 0 minus 2 times 1. So that's going to give me a minus 2, right? Plus the k component. And remember, the k component is going to be cross multiplying these two and these two, so I'm going to end up with 0 again. So it's going to be 0 times 0 minus 1 times 0. So that's going to give me a 0 again. So and all this is in units of kilograms meters squared per second. And what do we end up with? The only non-zero one is we have a minus minus 2, so it's 2.00 kilograms meters squared per second in the j hat direction. So there it is. That's how you calculate the angular momentum for that little ball moving along the x-axis around point P. I just want to show you an alternate way to do it real quick. The other way of doing this gets you the same answer is, let's just do it in terms of the magnitude. So L, the magnitude of L is R times M times V times the sine of the angle between R and V. And if you look over at the diagram, the angle between R and V is 90 degrees, right? So that's 90 degrees, so that just gives you 1. So when I plug in all the value, when I plug in R, M, and V, I get 2.00 kilograms meters per second squared. So it gives you the magnitude. That's a 0. One more thing. This here tells us that the angular momentum points in the j hat direction. So what does that mean? Well, the ball is moving to the right, but we're considering it as, at this instant, rotating around this point. So you can think of it as, at this instant, we're saying what's the angular momentum, so it's sort of rotating around the y-axis, is what we're thinking. And our answer gives us a vector that points along the y-axis. So the magnitude of the angular momentum is this, and the direction of the angular momentum actually just points along the axis of rotation. So this is the axis of rotation, so it's rotating around the y-axis, the j-axis. And one way to think about it, one way to figure it out is something called the right-hand rule. If you look at the diagram, and you take your right hand and you point your thumb of your right hand along the y-axis, then your fingers sort of curl around in a circle that goes around the y-axis, and that's the relationship of the axis. Your thumb points the direction of the angle of rotation, and your fingers curl around your hand and show you the direction that the ball is moving around it. So let's do the same problem, except this time we want to do its angular momentum around the origin. So in this case, it's slightly different. Now, before we found the angular momentum around this point, but now we're going to find the angular momentum around the origin. So it's rotating around a slightly different point. So let's write down our R vector. So R vector is a vector that points from the origin to the ball. So the R vector here, we want a vector pointing from the origin to the ball. So it's going to be 1 in the I direction. So it's going to be 1 meter I hat plus 2 meters j hat, right? So that's this vector here pointing from the origin to the point. We still have the same mass, it's 0.200 kilograms, and the velocity vector is the same. It's we'll put in the sig figs at the end. It's 5 meters per second in the I hat direction. And I have one tiny error here. This is, if you look at the R hat, it's not I and J. It is the 1 meter is in the j hat direction, and the 2 meters is in the k hat direction. There we go. That's more like it. Now to do the cross product, to find the angular momentum vector. So the angular momentum is R cross P. And once again, you put I, J, K. The units outside, you're going to pull out the units, it ends up being kilograms meters squared per second. So let's put in the, first, the momentum is going to be it's going to be, when you do mv, right, it's equal to 1 kilogram meter per second in the I hat direction. So let's see. First row is my position vector, which is 0, 1, 2, right? 1 along the y-axis and 2 along the z-axis. And my momentum vector is going to be 1, 0, 0. So when I do this cross product here, you have I, so the I components is going to be cross multiplying those two things. So it's going to be 1 times 0, so it's just going to be 0, minus j hat, and the j hat is going to be cross multiplying that times that minus that times that. So we end up with a 0 minus 2 again, so it's similar to what before, so we end up with minus 2. And then the k hat direction, we're going to multiply, this times this. So we have 0 minus 1. So we end up with a minus 1 here. And that's all in kilogram meters squared per second. So our final answer then is going to be 2.00 kilogram meters squared per second j hat minus 1.00 kilogram meters squared per second k hat. And that is our angular momentum for this ball around the origin. So here's another example, and I'm also going to take the opportunity to introduce another way of thinking about torque. At the instant shown, a 1 kilogram bug, that's a very big bug, has position, velocity, and a force on it as shown. So it's in the xy plane. The z-axis is pointing out of the plane. And we're going to find the magnitude and direction of the angular momentum of this thing due to the velocity and the motion, and the magnitude direction of the torque due to the force. So if you look at this thing, the angular momentum is going to be sort of counterclockwise-ish, and the torque is going to be in the opposite direction. So let's just do a couple of quick examples here. So first I'm going to write down the r vector. So let's write down our knowns. So our r vector, so we want to break this r here into x and y components. So this is going to be 2 cosine 40 degrees, and this is going to be 2 sine of 40 degrees, right? So it's going to be 2 cosine 40 degrees I hat plus 2 sine 40 degrees j hat. That's all going to be in meters. And we can see that our velocity vector is pointing straight up, so that's just in the j hat direction, right? So that's just going to be 1.5 meters per second upwards. For later, the force is going to be a positive x component and a negative y component, right? So it's going to be 3 cosine 30 degrees in the I hat direction, and then there's a negative y component, so 3 sine of 30 degrees in the j hat direction, and that's all going to be in newtons. What else do we have? Oh, we have the mass of this little bug. Do we? Yeah, it's 1 kilogram. It's a big old bug. We kind of have everything we need. We can get the momentum, and so the momentum vector, well, let's just write it down real quick. The momentum vector is just v times m, right? So it's going to be 1 kilogram times all those times the v. So it's going to be 1.5 kilogram meters per second j hat. So now for A, we can calculate the angular momentum. The angular momentum is going to be the cross product of I, j, and k components of everything. So the first row is going to be the r component, the r components, right? So this is going to be 2 cosine 40 degrees, and the j component is going to be 2 sine 40 degrees, and this is going to be 0. And then it's all the components of the velocity, or no, of the momentum. So, and that's pointed just in the j direction. So it's going to be 1.5 here, and this all works out to kilograms meters squared per second. And when you work everything out, you get about 1 point. Let's do an extra sig fig for now. Extra sig figs, kilograms meters squared per second in the k hat direction. Okay. So that is the angular momentum of this bug around the origin. Next, we are going to look at the torque. Now, we learned the torque before as Rf sine theta, but you can write it in cross product form. And remember, what's the direction of the torque? Well, it's going to be, well, before we do that, let's go back here. This here is the angular momentum, and its direction is k hat, so it's pointing out of the page. That means that this bug is rotating around an axis. Its angular momentum is around an axis perpendicular to the page, so it's sort of going, its angular momentum is sort of rotating around an axis like this. The axis just points around, the direction of the angular momentum points in the direction that it's rotating around, or the axis that it's rotating around. Same for the torque. We're going to get a direction for the torque, and that's just going to point in the direction of the axis about which the force is exerting a torque. So torque is R cross F, and it's similar to what we do with the cross product for angular momentum. So, for R, I would do the 2 cosine 40 degrees and 2 sine 40 degrees and 0, and this ends up being 1 Newton meters out here. And then we put in the force vector, which is 3 cosine 30 degrees and negative 3 sine of 30 degrees and 0. And you notice here, when we do the cross for the I component, it's going to be 0, because you're multiplying something times 0 in both cases. And we do it for the j component, it's also going to be 0. The only one that's not going to be 0 is going to be the k component there. And we cross multiply all that and plug in for our sine values. We end up with minus 5.64 Newton meters k hat. So that's a torque around the z-axis, but in the opposite direction. That torque is sort of going against the direction that it's moving. And that makes sense given where the force is pointing compared to the velocity. So, next problem. Or next thing I want to talk about. We rewrote force, if you remember, as d momentum dt, right? A force leads to a change in momentum. So it's not surprising that you can show that a net torque on something leads to a change in angular momentum. The torque and angular momentum are defined with respect to the same point, usually the origin. And what this is sort of another way of writing Newton's second law, right? The vector sum of the torques acting on a particle is equal to the time rate of change of the angular momentum of that particle. You add up all the torques acting on something, and that's going to tell you how fast the angular momentum is changing. Very similar to what we saw before for Newton's second law. So let's apply that to a simple example. Here I have a particle with a moment of inertia of 2 kilogram meter squared, and I have 3 torques acting on it. And I'm just going to change this to a j hat, just to make it a little bit simpler. So we have 3 torques acting on it. So if we want to find part A, we want to find the rate of change of the angular momentum. We just find the net torque, and that's equal to the rate of change of angular momentum. And then we're going to use that to find alpha. Just remember that the net torque is equal to I alpha. So once we find the net torque, we can find alpha. And this is, of course, similar, just as a reminder, the net force is equal to ma. It's just the rotational version of that. So first, let's do part A, where we need basically our dl dt, which is what we want, is equal to the net torque. So it's just equal to torque 1 plus torque 2 plus torque 3. So if we look at the there's 2 x components. They add up to 20 Newton meters in the I hat direction. And then we add up all the j components. There's a 12 and a 15. So that adds up to 27 Newton meters in the j hat direction. So that's our answer to A. It's just the rate of change is the net torque. Now for B, we want alpha, right? So we have that net torque is equal to I alpha vector. So alpha vector is going to be equal to the net torque divided by the moment of inertia. So basically, given that our moment of inertia is 2, we just divide the net by 2. So just divide this by 2, and that's our acceleration vector, which will have units of radians per second squared. So we end up with 10 radians per second squared in the I hat direction, plus 27 divided by 2 is 13.5 radians per second squared in the j hat direction. Okay. So if we have angular momentum of several particles all moving together around some common thing, the total angular momentum is capital L. We usually represent it with capital L. And you add them all up together. Now the rate of change of this net angular momentum of that whole thing will be equal to the sum of all the net torques, of all the torques. In other words, for a system of particles, the net torque is equal to the rate of change of the momentum of the whole thing. The net external torque acting on a system of particles is equal to the time rate of change of the system's total angular momentum. Okay, so we're sort of generalizing it to lots of particles. So I would like to extend this to a rigid body. In other words, if we consider every little point of a solid object as some sort of delta m, and we add up the angular momentum of each little individual piece, and we add them all up together, then our angular momentum is going to be equal, and they're all moving together, so they're all going to have the same angular velocity. That's the nice thing about this. So if they're all moving together, you can factor out this angular velocity thing, and they're all going to have the same angular velocity, and that means we can just add up all the angular momentum of all the individual parts. And so the sum of all this is the moment of inertia of the body, and we have a whole chart for the moment of inertia for various solid bodies. And therefore, we can simplify this whole thing to the angular momentum for a rigid body with a fixed axis, L, is its moment of inertia times its angular velocity around that axis. So if I have this blob here and it's rotating around the z-axis, if I know the moment of inertia of that blob, and I know how fast it's rotating, then I know the moment of inertia of that blob. And here's sort of a comparison again of all the things we've seen so far, right? Force in its rotational version torque, linear momentum in its rotational version angular momentum, for individual particles and for sums of particles and for a solid object. Newton's second law in momentum form, Newton's second law in angular momentum form. And next thing coming, of course, is there's going to be a conservation of angular momentum, just like a conservation of momentum thing. So first, let's just calculate the angular momentum of a 50 kilogram solid sphere with a radius of 30 centimeters. Okay, and it's rotating at 1,000 RPM. So why not? We can calculate this. First thing we need is the moment of inertia. So for a sphere, for a solid sphere around the center of mass, you look it up on the chart. That chart will be available to you when you need it. It's 2/5 mr squared, where the mass is 50 kilograms and the radius is 30 centimeters or 0.300 meters. And so if I plug everything into there, my 50 kilograms and my 30 centimeters, I end up with about 1.80 kilogram meters squared. We also need our angular speed, right? And it's given as 1,000 RPM. So 1,000, that's revolutions per minute, right? But we want to put that in radians per second. So let's see, what's one revolution? Well, that's 2 pi radians. And then we want to convert that minutes to seconds. So 1 minute is 60 seconds. And when I figure that out, I get 100 pi over 3 radians per second, which works out to approximately 104.7 radians per second. So that's the moment of inertia and the angular speed. So now we can use that to find finally the angular momentum. So it's just going to be I times omega. So if I multiply those two things together, I get approximately 188 kilograms meters squared per second. So that's our angular momentum for a solid sphere rotating around that axis. Now let's say we added a second sphere and we attach it to the first one, and we're rotating around the axis of this one. So now we need the moment of inertia of this whole thing. So sphere 1, sphere 2. So the moment of inertia is going to be the moment of inertia of sphere 1 plus the moment of inertia of sphere 2. The moment of inertia of sphere 1 is easy. That's just the same as the first one, right? It's going to be 2/5 mr squared. The moment of inertia of sphere 2, we have to use the parallel axis theorem, right? This distance here is 2r. So we need the moment of inertia through the center of mass, which is 2/5 mr squared, plus m times the distance here, this distance h. So it's m times 2r squared. And you see there's an mr squared in each term here. When I collect this together, it works out to 24/5 mr squared, which when you plug in your values is 21.6 kilograms meter squared. Omega is going to be the same as before, right? It'll be 100 pi over 3 radians per second. And then we can use that to calculate the angular momentum for this new situation. And so it's I times omega, and it's going to be a much larger angular momentum, right? It's rotating at the same speed, but there's a lot more mass, and the angular momentum is much higher. So that's just calculating angular momentum for two situations. So here's a kind of a fancy one from the textbook that I thought would be a good sort of overall calculation of angular momentum. We have some object constructed from a hoop of radius r and mass little m, and a square made out of 4 sides, and each side has a length r, and each side we're going to treat each side as a thin rod. And so there's 4 thin rods and a hoop, and and it's rotating with a period of 2.5 seconds. So first we need to find the moment of inertia of this object, and then we need to find its angular velocity, and then we can calculate its angular momentum. So first let's find the rotational inertia of this thing. Well, the rotational inertia is going to be the rotational inertia of the hoop plus the rotational inertia of the square, which is made up of 4 pieces. Okay, now the rotational inertia of a rod, so a thin rod, so let's say here's my thin rod. The rotational inertia of a thin rod here, if it's thin, then the rotational inertia when it's rotating around an axis through its center is 0, because it's so close. If it's so thin that everything is on the axis, its moment of inertia is 0. But the moment of inertia of a thin rod around like this, if it has r as its length, right, then that moment of inertia ends up being, these are on the table, 1/12 mr squared. So we're going to have to calculate, we're going to have to apply the parallel axis theorem a couple times, but let's do them. And for a hoop, the moment of inertia for a hoop is around its center of mass, is 1/2 mr squared. So let's see. So for the hoop, we have to do the parallel axis theorem because it's not going through the center of axis. So it's going to be the moment of inertia through its center of mass plus m times the distance. So how far is the axis from the center of mass? Well, it's a distance r. So plus mr squared. So that's the moment of inertia for the hoop. Now for the square. So there's 4 sides to the square, right? The right side, the moment of inertia for the right side, plus the moment of inertia for the left side, plus the moment of inertia for the top side, plus the moment of inertia for the bottom side. Let's see. Here we have 3/2 mr squared from that first thing. So the right side is right here. It's on the axis, so that one is going to be 0. The moment of inertia for the left side, we're going to use the parallel axis theorem. So it's 0 plus the distance. How far is this one here, the left side, from the axis of rotation? Well, it's distance mr squared, right? Now, plus, now the moment of inertia for the top and the bottom, these 2 horizontal ones are going to be the same. So let's figure it out for one of them and multiply it times 2. So it's the moment of inertia, which is through the center of mass, 1/12 mr squared, plus how far did it move from its center of mass? Here's the center of mass. It moved a distance r over 2. So it's m times r over 2 squared. And that is a lot. So that's the moment of inertia for the hoop plus each of the 4 sides of that square around that axis. And when you add them all up together, it simplifies to 9/16 mr squared, which works out to about 1.6 kilogram meter squared. So now we have the moment of inertia we need the angular velocity. So to find the angular velocity, we are given that its period of rotation is 2.5 seconds. So we can get the angular velocity from that. The period of rotation means that it takes 2.5 seconds to go through one whole rotation. So remember, angular velocity is change in angle over change in time. So one whole rotation in 2.5 seconds, a whole rotation is 2 pi radians, right? So it goes through 2 pi radians in 2.5 seconds. So when we figure that out, so that's going to be our, well, we'll just leave it like that for now. That's going to be our angular momentum. So that's going to be our angular velocity. So now from that we can calculate our angular momentum, right? Angular momentum L is going to be I times omega. So I plug in my value for I plug in my value for omega, and I get approximately 4.0 kilograms meter squared per second. Here's another great example. Two disks are connected via a belt, as shown. And one of the disks is spun, the larger disk here, has radius 2r, mass m, and it's rotating at angle omega. So this is rotating at a certain angle, a certain rate of, omega, whatever radians per second, radius 2r, mass m, and it's attached by a belt to this one. So this is going to make the smaller one spin, and it has half the radius and 1/4 of the mass. So what is going to be the angular velocity of the small disk as a function of the larger disk? So one thing we can do to figure this out is note that if we look at this point here, the belt here, the point on the belt is moving at some speed v. And that speed v is going to be the same everywhere. So it's going to be v here, it's going to be v here, it's going to be v here. Every belt at that moment, in fact, on the point here, is going to be v. So if I can find what v is on one, it'll be the same as the other, and I can use that to find the angular velocity of the small disk. So for the large disk, omega is equal to, remember, omega is equal to v over the radius for a point on the edge. So the radius is 2r. Okay, so we have an expression for the angular velocity. So that means that the velocity at every point along the whole belt at every point is going to be 2r omega. Now we can use that to find the angular velocity for this one. We'll say that this one here is rotating with omega prime. So what is going to be this angular velocity? Well, it's going to be the same velocity, but it's going to be divided by r, right? So I'm going to plug in for the velocity, this equation here that we just found. So it's 2r omega over r. So that means the r's cancel. We end up with 2 omega. So this is sort of a simple gearing thing that you may have seen before, right? This thing is spinning a certain angular velocity, and because this has half the radius, it's going to be rotating at twice the angular velocity. And now that's sort of part A. And now I can figure out the angular momentum of these two things. So what's the angular momentum of the larger one of mass m? Well, it's going to be the moment of inertia of this large disk times its angular velocity. So moment of inertia is 1/2 m times r squared. In this case, it's 2r squared times omega. So our final answer is 2m r squared omega. What about the smaller disk, which has a mass of 1/4 of that? So it's going to be the moment of inertia of the smaller disk times its angular velocity. And I do 1/2 times the mass, which is m over 4, times the radius, which is r squared, times its angular velocity, which is 2 omega. And I end up with 1/4 mr squared omega. So you notice that this one is 8 times more angular momentum than the small one. Even though the smaller one is moving faster, the larger one has a lot more mass. And so that's sort of the relationship between those two objects. So since we have a new version of Newton's second law, we also have a new conservation law. Basically, if there's no external external torque on it, then the angular momentum is going to be a constant for this isolated system. In other words, the angular momentum at the beginning is going to be equal to the angular momentum at the end. Oops. If the net external torque acting on the system is 0, the angular momentum of the system remains constant no matter what changes take place inside the system. And we can do that for each separate axis, right? But we're just going to look around one axis for now. So the angular momentum around at the beginning will be equal to the angular momentum at the end, and we can use this to solve some basic conservation of angular momentum problems. So one of the most famous ones, of course, is the ice skater. If the ice skater is spinning with their arms out, when they pull their arms in order to conserve angular momentum, the rotational inertia changes. And we have some videos for that. And the videos will be linked in the notes to this video. So now let's consider some dude who has a moment of inertia, that is 12.5 kilograms meters squared, and he's holding two masses. And let's say each mass is 10 or two. We'll call them weights, and each weight is 10 kilograms. All right, and he's holding them 1 meter out on either side of him. And he's initially rotating at 2 pi radians per second, which is the same as 1 revolution per second. So he's spinning pretty fast. He's holding his arms out. Arms are getting tired. So what he's going to do, he's going to bring the weights in. So he's changing his moment of inertia. And basically he's changing his moment of inertia, so the angular velocity is going to compensate by speeding up. So let's figure it out. So the angular momentum that we're given here, the moment of inertia that we're given here is not this moment of inertia here is just for the dude. We need the moment of inertia for the whole thing, right? So the initial moment of inertia is the moment of inertia for the dude plus the moment of inertia for each of the weights. So there's two weights like this, right? So the moment of inertia for the dude is given as 12.5 kilograms meter squared, and then it's 2 times the moment of inertia of the weights. And we're going to treat them as little points. So there's 2 of them, their distance r, we're going to call this r, their distance r 1 meter from the center, so it's going to be 2 times mr squared. That's the moment of inertia of a point about an axis of rotation, right? They're rotating around this axis here. So this is 12.5 kilograms meter squared plus 2 times 10 kilograms times r squared, so it's 1 meter squared, and that works out to about 32.5 kilograms meter squared. So that's for the initial situation. What about the final situation? Well, it's similar, except instead of the 2 weights being 1 meter out, they are at r prime equals 0.2 meters out. So it's going to be similar. We're going to assume that him moving his arms in doesn't change his moment of inertia very much. But now it's the new moment of inertia of the weights. So it's going to be, 12.5 kilogram meter squared plus 2 times the mass times this new distance r prime squared. And when you work it out, that works out to only 13.3 kilograms meter squared. So the moment of inertia gets quite smaller when he does that. So let's do conservation of angular momentum. So the initial angular momentum is equal to the final angular. Nope, I did that wrong, sorry. The initial angular momentum, not the initial moment of inertia. The initial angular momentum is equal to the final angular momentum. So it's going to be I initial omega initial equals I final omega final. And this is what we're trying to find. How fast is it going after he brings in his hand? So omega final is going to be equal to I initial over I final. It's going to be the ratio of their moments of inertia times the initial. And I plug in my numbers and I get 2.44 revolutions per second is the final moment of inertia, and the initial moment the final angular velocity. The initial angular velocity was 1 revolution per second. So by bringing those weights in, those 10 kilogram weights in, he started moving 2.5 times faster. Another example, let's say I have two disks that are spinning. Disk 1, right here, has a moment of inertia of 3.3 kilogram meter squared, and it's rotating at 450 revolutions per minute clockwise. Disk 2 has twice the moment of inertia, 6.6 kilograms, and it's rotating with a speed of 900 revolutions per minute counterclockwise. I drop one on top of the other, they become one disk, they immediately stick together. What's going to be their final angular momentum? Well, one's turning 450 one way, the other one's turning 900 the other way. It's going to end up turning one way or the other. So let's quickly write down everything we know. The moment of inertia for disk 1 is 3.30 kilograms meters squared. The moment of inertia for disk 2 is twice that, 6.60 kilograms meters squared. And the final moment of inertia is the sum of those two, right? Because they're stuck together. So it's just going to be the sum of those two, so 9.90 kilograms meters squared. And we have the initial angular velocity of the bottom one, it's 450. We're told it's counterclockwise, revolutions per minute. In some cases, you can leave this in revolutions per minute, and you're going to see that we can do that in this case. And we're told that the other one is rotating the opposite direction, so we're going to say minus, and I'm going to change this from 900 to 600. I believe that's what the original question asked, to minus 600 revolutions per minute. And we're trying to find the final angular speed, angular velocity. So it's all about that L initial equals L final. So L initial is going to be the initial moment of the initial angular momentum of disk 1 plus the initial angular momentum of disk 2 is going to be the angular momentum of the final thing. So this is I1 omega 1 plus I2 omega 2 equals I final omega final. So omega final is equal to that. We'll just solve for omega final, right? And when I plug everything in there, I end up with minus 250 revolutions per minute. So that's basically it. The top one was spinning faster and had a lot more moment of inertia, so this sort of dominated. This had a lot more angular momentum than this, and so the final thing is not actually going to be spinning that way. It's going to be spinning in the opposite direction. Minus 250 revolutions per minute. One other example here that I think would be fun for you to do sometime. I will write down that you should consider doing this one and trying it out. So, just a quick note on gyroscopes. A non-spinning gyroscope, right? A gyroscope is basically, you can think of it as like a bicycle wheel attached to a stick, and if you get it spinning, it has angular momentum. But if it's not spinning and I attach it with a string to with a stick here to a support here, and I just put it on there, it's just going to fall down because gravity is going to act on it and pull it down. But if I spin it really, 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 really fast, it will not fall. It will sort of stay there. It develops an angular momentum pointing in this direction, and instead of falling, it sort of precesses. It moves in a circle around the stick here. So I have a video to this that you absolutely must watch. I will put it in the comments, sort of demonstrating this. I would do it for you in class if we could. You can show that the angular momentum of this rapidly spinning gyroscope, right, is I omega, I times the angular velocity. And the torque can only change the direction of L, not its magnitude, because the torque is always perpendicular to L. And so basically what the torque does is it just makes the direction of the angular momentum slowly move around. It precesses instead of toppling over. Okay, so the only way its direction can change along the direction of the torque without changing its magnitude is if it rotates around that central axis. And that's sort of related to conservation of momentum. And you can show that the precession rate, how fast it moves around in a circle, is related to the mass and gravity and the radius and the moment of inertia and how fast it's rotating.